this video, we're going to explore this graph. We're going to look at how the probability of failure at a mean life of various Weibull function changes as a function of the shape parameter of the Weibull function itself. So we've considered Weibull function which include infant mortality, so we start off with a beta of 0.4. Includes also random failure, we got a beta of 1, and then we got various levels of degradation. So gentle degradation all the way up to a very pronounced degradation. And we can see how the failure rate, the probability of failure at the mean life changes as a function of the shape parameter of the distribution. And we can see that with a beta of 0.4 we have a probability of failure at mean life of about 80%, and this drops as we increase the shape parameter. This drops below 50%. we are about 45% at with a beta of 10. And obviously this is different from, say, the exponential distribution hasn't got a shape parameter, and the probability of failure at mean life is a fixed one at 63.21%. And in fact, the mean life of the Weibull function is dependent both on the scale parameter eta and the shape parameter beta, and is given by this relationship eta multiplied by the gamma function of 1 plus 1 over beta. So let's have a look how we can create this function. So we go now into a Weibull folio, but we don't use this blank piece of paper, but we've actually used the general spreadsheet. We use the general spreadsheet where we've already configured our data. We don't use the Weibull folio because we would have to configure so many different functions according to our beta. But we don't want to use that. We want to be as flexible and as minimalistic as we can. So we fixed an eta of 10,000 hours, and as we say, we do a range of beta from 0.4 to 10. So by doing that, we got infant mortality all the way up to fast wear out. And then we compute the 1 plus 1 over beta, which is an element of our mean life. And then we use the gamma function, but we don't use this function wizard because the function wizard gives us some functions that are linked to the actual folio, but the folio where we got our data, we don't have any data on that. So we use instead this insert function that enables us to insert mathematical, statistical, engineering function, and in fact we are looking for a specific function, and we go searching, and somewhere here we find possibly under the statistical one, we find our gamma function. So by doing that, we can, like we've done here, we simply calculate the gamma function of our cell 1 plus 1 over beta. Once we've done that, we've seen from the formula in the previous video that the mean life is simply the eta multiplied by the gamma function of 1 plus 1 over beta. So by doing that, we've calculated the mean life, and the last element is basically inserting the probability of failure of the Weibull function that will take into account the various beta, will be calculated at the various mean life, and taking into account also the scale parameter, which is fixed. And we can see that, as we saw on the graph as well, for infant mortality we got a probability of failure of over 80%, and this one drops all the way down to about 45% for our beta of 10. And obviously there is a point where it hits 50%, and it's 3.4, we got 50.08, and if we go digging a little bit more, we find that it is actually 3.44, and we know from theory that 3.44, the Weibull distribution becomes, the shape of the Weibull distribution becomes a symmetrical one, becomes a normal distribution. And in fact, for a normal distribution, the probability of failure and probability of survival is exactly 50%. It's a symmetrical distribution, therefore it's 50%. And the graph is simply the beta as a function of probability of failure. And that's it.